Continuing with our notes from section 9.2, we are looking at finishing up on talking about telescoping series, where we have terms that are close to each other and also in a way where they're subtracted from each other, and we have values that will eventually cancel out down the line. So if we test this out here, if we replace n with 1, we get 1 over 1 minus 1 half, plus, replace n with 2, so we get 1 half minus 1 third, and then 1 third minus 1 fourth, 1 fourth minus 1 fifth, so on and so forth. And we see that the negative 1 halves cancel out, the 1 third cancels out, the 1 fourth will cancel out, leaving us with just 1. And so the sum will converge simply to 1. We can also write, looking at example 6 here, writing a series in telescoping form. Find the sum of the series of the summation of 2 over 4n squared minus 1. If we expand the denominator, we get 2n plus 1 times 2n minus 1. And we can do partial sum decomposition to help us break this down into the sum of 2 fractions. So one way we can do this is we know that we have a fraction with 2n plus 1 in the denominator, and we have another fraction with 2n minus 1 in the second denominator. The way that we can go about doing this is for 2n plus 1, we can decide what value will make 2n plus 1 0, and the value that makes 2n plus 1 0 is negative 1 half. So then we're going to plug negative 1 half into our expression. So if we cover up 2n plus 1 and then replace the remaining n value with negative 1 half, we're going to get the 2 times negative 1 half, which is negative 1 minus 1, which is negative 2. So 2 over negative 2 will just give us negative 1. And so that will be the value that we put in the first fraction. Okay, and we ignore this 2n plus 1 because this has already been covered up using the n value that causes it to go to 0. Now for the second 2n minus 1, we decide what n value will cause that 2n minus 1 to go to 0, and that n value is a negative 1 half. So then we cover up the 2n minus 1, replace the n with a negative 1 half, and we'll get 2 times negative 1 half. The 2n minus 1 here is a positive 1 half, so we're going to plug positive 1 half into the remaining expression after we cover up the 2n minus 1. So 2 times 1 half is 1. 1 plus 1 is 2. 2 over 2 is 1. So our numerator for this second fraction will simply be 1. And then we have our term split up into 2 parts, and we can see if this will be applied for telescoping series. If I replace n with 1, I'll get negative 1 third plus 1. If I replace n with 2, I get negative 1 fifth plus 1 third, negative 1 seventh plus 1 fifth. And if we write out these terms, we can see that eventually the negative 1 third will cancel out, the 1 fifth, negative 1 fifth will cancel out, the 1 seventh will show up later, which will eventually cancel out. So every term will cancel out except for this 1. Okay, so the sum will converge to 1. We do have to be careful with these types of problems. Sometimes it may not just be the first term. We may need to write out a couple of terms of sequences, sometimes maybe more than 3 or 4, in order to see, just to convince ourselves that everything else will cancel out. So we do sometimes have to be a little bit careful in having to make sure that all of the values have been accounted for. Okay, so next topic is geometric series. So series of the form of a times r to the n are called a geometric series with a ratio of r. Geometric series with a ratio of r will diverge if the absolute value of r is greater than or equal to 1. However, if the absolute value of the ratio is between 0 and 1, then the series will converge to the sum given. And the sum is a sub 1 over 1 minus r. Notice that the geometric series will diverge if the ratio is 1. So even if it is 1, it will diverge and greater than or equal to 1. So in order for a series to converge, the ratio has to be less than 1. So we have to make sure we're careful about that value 1. Okay. This is one of the few tests where we can find the sum once we determine that the series converge. Usually, we're going to talk about a lot more tests, but usually we're more concerned about determining whether a series will converge or not. Finding the sum is sometimes not that easy, but with geometric series we can always guarantee that we can find a sum as long as the series converge. With the other ones, it may not be as easy to find, and sometimes we may have to resort to finding an approximation using partial sums. Okay, let's look at some examples here. The summation of 3 over 2 to the nth. Now this is in the form of a geometric series. We see the base 3 halves raised to the nth power, so this is kind of like an exponential form here with geometric series. So, however, the ratio is 3 halves, and 3 halves is greater than 1, so we know that the series will diverge because this 3 halves is causing each term to keep increasing. Okay. This next one here, 3 over 2 to the n, we can rewrite this by pulling the 3 out, making this 1 over 2 to the n. And 1 over 2 to the n, the same thing as 1/2 raised to the nth. And if we have it in this form, then it's easy to see that the ratio is 1/2, and ratio of 1/2 is less than 1. And as long as the ratio is less than 1, we know that if it is a geometric series, this series will converge. And if we want to find out what this series will converge to, meaning the sum after everything is added together for this infinite series, we do a sub 1 over 1 minus r. So a sub 1, the first term in this series, will be 3 halves. That's a sub 1, all over 1 minus r. So ratio is 1/2. 1 minus 1/2 is 1/2. 3 halves over 1/2 will produce a value of 3. So our series will converge to a sum of 3. Okay, the next section is concerned with determining whether a function converges or diverges. There are several tests for convergence and divergence that we will have to know. The first is this, nth term test for divergence. So this is usually the first test that we do regardless of the series that we see, just because this is a very fast test to do, and it's one of those things where we want to test this because it could save us a lot of time. Okay, but there are restrictions to this, and we do not want to misuse this nth term test for divergence. It's easy to misuse this, and I'll talk about why. This test does not test for convergence. Okay, so we got to keep that in mind. And here's the nth term test. It says if the limits of a sub n of our rule of sequence as n approaches infinity does not equal to 0, then the summation of a sub n diverges. So it's a simple test, but it's easy to misuse. So if the limit does not equal to 0 of the sequence is not equal to 0, that means this sequence is not decreasing fast enough where it will allow for the series to converge. So therefore, if the limit does not equal to 0, then we can say we know if we add up all the terms, there's no way it will converge to a value. Okay. However, the converse of this is not true, which means that if we are to show that the limit of a sub n equals 0, then this test is inconclusive, because just because the limit of our sequence is approaching 0, it's not strong enough to tell us whether the series will converge or diverge. Okay. So again, if the limit of the sequence as n approaches infinity equals 0, then this test is inconclusive, and we're going to have to investigate further to determine whether this series converge or diverge. Okay, so this is again only a one-way test, and we do want to make sure that this is the first test that we check. It's a bit of a time saver, and it's just a good habit to get into. Hey, let's look at number 9. So the summation of 2 to the n. Now we can simply, let's do the nth term test here. Limit of 2 to the n as n approaches infinity. This will go to infinity, so the limit does not equal to 0, and the limit of the sequence does not equal 0, and we can simply say, therefore, by the nth term test, our sum will diverge. Okay. The second here, number 10, n factorial over 2n factorial plus 1. And the limit as n approaches infinity is equal to 1/2. Right? If we think of these as values or variables with the same degree, we can take the leading coefficient, which is simply 1/2, since this is n approaching infinity. And 1/2 does not equal to 0. So therefore, this limit is approaching 1/2. However, it is not decreasing fast enough in order for this series to converge. So because through the nth term test, because the limit as n approaches infinity for the sequence does not equal to 0, we can simply say that the series diverge. Okay. All right, the summation of 1 over n as n approaches infinity. This here, we find the limit as n approaches infinity for 1 over n. Now this limit does equal to 0. However, what do we say? That the converse of the nth term test for divergence is not true. So just because it's equal to 0, what we can say is, well, the nth term test for divergence is not conclusive. So this may or may not be convergent. And based on the nth term test alone, we cannot make a conclusion for convergence. But just for future reference, this 1 over n does end up being divergent, even though the limit of the sequence as n approaches infinity is equal to 0.